This idea that just because we can understand a model, does that mean it's actually good for inference? And I think that's a mistake we make often, kind of conflating understanding with inference, at least causal inference. All right, so today's plan, we're going to kind of talk about what I would call kind of a general predictive modeling framework. A lot of this is from Max Kuhn's Applied Predictive Modeling book. We're then going to kind of dig into the nuts and bolts of some machine learning stuff. We're going to take a quick aside into causal inference in the spirit of last week's Nobel in economics. And then we're going to talk about salmon forecasting. So for those of you who are just tuning in for the salmon forecasting, you can mute me for a while here. All right, so the predictive modeling framework. Many of you who've kind of seen me talk about this have probably seen this figure before. This is again from Max Kuhn's Applied Predictive Modeling book. And this is kind of the core, right? This is the idea that I think kind of underpins the difference, really, in my opinion, between a predictive model and an inferential model. And it comes down to kind of no matter what the engine you're using to do the prediction of machine learning, a neural net, a random forest, a linear regression, whatever, it's about kind of putting it through these paces here, right? Where the idea is we've got some data. We then split that data into a testing and a training set. And then in a kind of canonically perfect world, right, we take that testing data, we lock it in a crate, we bury it in the bottom of the ocean, and we don't touch it again until we're ready to, like, unveil our final model. And in theory, if, whatever result we get, that is the only result we ever get. That's not really how this stuff tends to pan out, but that's kind of the idea. And then from within the training data, we take resamples of our training data, and then we split that into a series of kind of, baby training and testing sets, which kind of confusingly get called like the analysis and the assessment split, where the analysis is the training, the assessment is the testing. I don't love that. It's a little confusing, but that's the idea there. So this is kind of the core thing that I think, I'm usually looking for in evaluating kind of any predictive modeling framework and kind of the bones of anything I'm trying to do in that area there, right? So why do we have to do all of this splitting? Well, we have lots of ways we can assess aspects of an inferential model, kind of our traditional statistics, right? P-values, insert long rant here. We can have a discussion about that some other time. But, confidence, credible intervals, whatever we want to call them, information criteria, which is really kind of a proxy for predictive power. But the key with all of these, right, is that they're all kind of leveraging statistical theory to say, just conditional on the data that we fit to, we're kind of making a statement about the quality of that fit. Usually, again, where the quality is judged by inference, though, again, information criteria is kind of this fuzzy thing. It's really more of a predictive metric there. A predictive model, on the other hand, really only has one means of validation. That's out-of-sample predictive power. Right, so you've all kind of seen the crazy flow chart of, all like the crazy frequentist stats testing, kind of if it's this, it's that, if it's distributed this way, go down this way, right? With predictive model, the nice thing about it is it's kind of simpler, right? It's just kind of the proof is in the pudding, can you build a model that is demonstrably good, and you can talk about whatever the metrics of good you want to be at predicting out of sample, right? The reason this out of sample thing is so important, though, is that many predictive models, in particular things from the machine learning world, often have many, many, many more parameters than they do data, which, that seems like the most basic no-no you can possibly have in a statistical model, from our original training, right? And what this kind of means from a practical sense is this kind of out-of-sample splitting regime is really our only valid test for differentiating between a model that's just kind of memorizing the data, if you will, because it can certainly do that with the amount of parameters that it has, versus actually learning meaningful predictive correlations that exist within the data. Right. Okay. Good predictive modeling requires that we spend some of our data budget then on holdout testing. And this is really not popular, right, when data are either hard or expensive to come by, right? Somewhere someone decided that about an 80-20 training testing split was kind of a good level for that initial split. I can't find the original paper that kind of did some stuff on that, but it's not like a hard and fast rule by any means. But that's kind of a general thing we're looking at there. And so that's often kind of, a beginning place there. If you're thinking about, well, is a predictive modeling framework something I can do here? Thinking about, do you have, 20% of your data that you're willing to basically spend on testing as opposed to actually fitting your model? which, again, can be very unpleasant, for, if your data are expensive or hard to get. And then the key thing that I focus in on a lot, right, is that then the design of this initial split needs to be really carefully designed to reflect the intended use of the model itself. And I think this is a thing where we mess up a little bit sometimes, right? Thinking about, is the point of this predictive model to do interpolation? Is it to do extrapolation? If it's extrapolation, is extrapolating in space, in time, both, across species? Like, what's kind of the actual thing you're trying to do there? And thinking about, how do you design your testing regime to reflect that? So to give a quick example of this, this is from a paper that's currently in review, where we're kind of going back to the well of evaluating catch-only models for a lot of reasons. The idea here, this is a machine learning model, a boosted regression tree, which we'll talk about later, linking attributes of catch history to trying to predict B over BMSY from RAM. We're not going to spend time on this. The really important thing here is to kind of notice these three panels here. This first panel on the left is the fit of this model to the training data, just as a whole, right? So if you look at that, you go, holy cow, R squared of 0.7, root mean squared error 0.5, like, just looking at that looks great. I have cracked this, right? We finally have like a good catch-only model predicting B over BMSY. The problem is that's not really how we would think about using a model like this, right? If we knew B over BMSY, we wouldn't need this. So we need to be able to test its ability to predict a fishery we haven't seen before. And so if we repeat this process with, say, just leave one out cross-validation, we see that now the performance plummets, but it's still okay. But even that might not be the right testing strategy, right? That might make sense if the goal is, say, I've got 10 assessed fisheries on the West Coast, and I want to fill in the gap on kind of this missing 11th fishery on the West Coast. But what if instead we want to use this model, train it on the West Coast, and predict Australia, New Zealand, and South Africa, which is kind of what this final split is here, right? And we see now, once again, our performance has dropped yet again from kind of even that leave one out performance. Both of these are valid, but kind of which one you want to use depends a lot on the actual question you're trying to touch on here, right? So designing that testing split makes a huge difference for doing a proper evaluation of what the predictive power of your model is going to be. So from there, you've got your training data, and now you have to split more. Why, right? Like, that seems like, are you kidding me? I already went through all this. The issue here, right, is we rarely just have one model we're considering, right? We're usually thinking about different parameterizations of a model, different error structures. In the case of machine learning models, we're often talking about a lot of different nuisance parameters that we'll talk about later. But our only way of judging a model is out of sample prediction. So if we're going back and forth with the testing data and the training data to make these kinds of decisions about which model do I want to use, should I include this polynomial, what should this tuning parameter be, you're not really actually using the testing data as a valid set anymore, right? You're kind of manually fitting to the testing data now. We can have a discussion about this. The more degrees of freedom you have, the less of an issue this all is. It really kicks in a lot, like with these big industrial models where it's like, their accuracy on an old model is like 95%. This new model claims to get them to like 95.5%, which can be a huge difference. And you're trying to like make sure that that difference is real, right? Maybe a little difference for the kinds of games we're talking about here, but it's still important. I'm going to skip past this part. Feature engineering, data pre-processing. Need to take care to quarantine your data on that stuff, but let's move on now. So to kind of pull that all together then, right, kind of the generic predictive modeling workflow that I try and follow and look for when I'm looking at papers, right, is split the data into training and testing, lock testing data in a vault under the sea, split training data into a series of analysis and assessment splits, e.g. using repeated B-fold cross-validation or something like that. Design all your feature engineering, design your candidate models, use the analysis and assessment splits to make any decisions to help each model be the best that it can be, fit the best version of each model to the full training data, and then finally assess the performance of that model on the testing data. In particular, kind of comparing that best fit from the training data to that best fit in the testing data and hoping it didn't go down all that much. If it did, you've probably got a problem. So you can see that that's a pretty involved process, and we'll talk about kind of how to go about doing this a little later here. But I think this is kind of the key feature here, right? This is what I think we're talking about when we talk about predictive modeling. predictive modeling doesn't mean, subbing in random forest for LM in R, right? It means thinking about how are you designing this entire kind of workflow in an effective manner. Okay. With that in mind, then let's take a moment and actually then dive into some machine learning models themselves, right? I keep saying there's nothing special about machine learning as a predictive model. You can use a linear regression as a predictive model, totally fine. That being said, machine learning models are really good at it for reasons we'll talk about in a bit here. And I think it's worth kind of spending some time talking about kind of the nuts and bolts of some of the most popular beasts here. Machine learning is a funny thing, right? Like it comes much more in many ways from kind of the engineering literature, right? If you read these papers, right, it's not, you're used to like a method stats paper is kind of building up from stats theory and kind of, working its way to kind of a final method there. And a lot of like the machine learning ones are kind of like, I wonder if I wrote an algorithm that does this. Oh, look, that worked pretty well. And then maybe someone later kind of reverse engineers the stats that kind of go behind it, right? But a lot of times it is kind of a version of piling a bunch of linear algebra together and seeing what happens and mixing around until things work, which is part of the reason they work and part of the reason people find them weird and scary. I think it's important then to spend a little time with the terminology here, right? A lot of times you'll probably hear machine learning and artificial intelligence kind of used interchangeably, oftentimes also with deep learning thrown in the mix if you want to get really fancy. I like this little Venn diagrammy thing over here from Deep Learning with R, which basically lays out the idea is that artificial intelligence is a very big field that kind of encompasses all these things. And it goes back a really, really long time. This is a neat quote from one of the earliest kind of computer scientist thinkers, Lady Ada Lovelace in 1843, who was talking about kind of these early mechanical computers and was pointing out that it has no pretensions whatever to originate anything. It can do whatever we know how to order it to perform. Its provenance is to assist us in making available what we're already acquainted with. And this is kind of, again, that's a little convoluted, but that's artificial intelligence, right? It's saying we have an idea and we can basically, tell a computer with a bunch of if-else statements, if nothing else, right? To kind of copy that idea, and make it real. A simple spam filter, right? If email contains words get rich quick, then spam, right? That's artificial intelligence. It sounds really fancy though, so people tend to use it when often what they're kind of really talking about is machine learning, which is this idea of basically instead of telling the model what the model structure is and estimating parameters, you feed the model answers and the machine learns what the structure of the model should be. That's kind of the big distinction there. Usually like in the literature on this stuff, if it's actually like a technical piece, it'll talk about machine learning, maybe deep learning. Kind of the more like general audience things tend to be, the more they'll kind of talk about their thing as artificial intelligence. When oftentimes, it's a fancy regression is what we're kind of talking about there. All right, there are lots of different machine learning models out there. There's at least 68 machine learning-ish models in the Parsnip package, which is kind of the workhorse for all this stuff in R. There's many, 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 many more out there. Given heavy industry use, there's a lot of incentive to develop a model that does marginally better in a specific situation, because marginal gains can translate into lots of money. And also, maybe cynically tweaking a model is a good way to get a degree, right? That being said, though, out of all of these, right, these three here, random forests, gradient boosted trees, and neural networks kind of are the workhorse. They're the ones you're going to encounter the most. And that you're most likely to use unless you're really diving into some very specific use cases here. All right, so random forests. You've probably heard these, you've probably used them. They're very common these days. I like this quote and I included it, a bunch of stupid trees learning to correct errors of each other. And then I thought about it and that's actually not correct. It's actually kind of what boosted trees are, so maybe ignore that. The nice thing about random forests is that they're just about where everyone starts in machine learning. They're often near the best performer, and they're very rarely the worst. And they're really hard to mess up too badly. They have a nice feature of they kind of have built-in out-of-bag predictions, out-of-sample predictions. But I think sometimes they can create a bit of a perception then that switching to kind of machine learning is as easy as subbing in, Ranger or random forest for LM. So a random forest is a forest of regression trees. If you've never seen these before, I think this is a very nice example of a regression tree from Nico Gutierrez et al. 2011. And this is the idea of, instead of kind of, defining a linear model a priori, you can ask the data to kind of learn a tree to help explains, in this case, for example, co-management success, where the top node of the tree is leadership, and then there's a split down here for sedentary, and so on and so forth. So the important thing about a regression tree is that it's a low bias, high variance estimator, right? That means that it's really good at kind of instantly like fitting the data in a really complicated way. But small perturbations to the data tend to kind of completely change the structure of the tree, right? Because it's dependent, right? If this top node changes, kind of all these bottom nodes probably have to change by default too. So what a random forest is, right, is an ensemble of trees. And to kind of give like the simple pseudocode for this, I'd recommend the Ranger package in R for kind of doing this. You basically, for every iteration M, or generate a bootstrap sample of the original data, train a tree model on this sample. For each split in the tree, randomly select K, where K is less than your total pool of original predictors, and then select the best predictor among those K predictors, and then partition the data based on that predictor, build the tree, you get a big ensemble of trees, and then the prediction for any one node is the average for that prediction across all the trees, more or less. Within that, then, a kind of a nuisancey thing about machine learning models are these parameters, these tuning parameters that have to be set outside the model itself. This is what the analysis assessment splits are. Most models have a few that they are much more sensitive to than others. For random forests, the big ones are this thing called mtry, which is the number of predictors that will be randomly sampled at each split, min n, the minimum number of data points in a node, and trees, the number of trees contained in the ensemble. A really nice feature of random forest is all that randomization earlier means you cannot overfit in the number of trees. The only downside to kind of having infinite trees is your model will just take forever to run, so it's a neat feature. But this is kind of where the devil in the details comes in machine learning models, is that you have to make these decisions outside of the model fitting process, and they can have a big impact on how well the model actually performs. And a nice feature of random forest is that they're kind of the least sensitive of anything to these factors here. Okay, so the next kind of by far most popular one we're looking at here are gradient boosted trees. And among these, extreme gradient boosting XGboost, which is kind of by far and away the most popular method, to the point it's sort of a name unto itself. This is a open source software project in R and Python, lots of other stuff, right? And it's by far the most popular kind of regression. If you're doing kind of regression-esque things, you're doing classification, you're trying to predict a number, that kind of stuff. To quote their website, it is battle tested. To pull from the Causal website, which if you're not familiar with Causal, it's a place that kind of hosts all these predictive modeling competitions. It's the most accurate modeling technique for structured data, wins tons and tons of Causal competitions, Conqueror of Worlds, Lord of the Seven Kingdoms, etc. It's it's the bee's knees. It's what everyone loves to use. It's very cool. So gradient boosted trees are a little bit different than a random forest. They're similar in that they're still using a bunch of trees, but the basic idea is you start with your base prediction, which is every single value is the average value of the response, and that's your initial prediction. You then train a tree on the residuals, the observed minus the predicted, for that specific for what you've got there, like relative to the mean in that case. You then find the best tree to kind of predict the residuals. You then add those residuals to the original prediction, train a new tree on the residuals from those two trees, and so on and so forth. So you're building the sequence of trees, each one kind of learning from the one behind it. Kind of weird, we can spend time if folks have questions on that, but that's kind of the gist of the idea behind XGBoost. There's obviously lots of nuance to the details there, but that's kind of what's happening there. So very neat, and kind of makes sense, right? It's literally, as the model's going along, it's like actively finding the parts of the data that it's worst at predicting and trying to get better at that. All that performance comes at a cost, though. In my experience, XGBoost is much more finicky than things like random forest. The key parameters here are a bunch more. You'll recognize some familiar ones like M, try, and trees, but you've also got this tree depth thing, the learn rate, loss reduction, sample size, stop iter, all these things that can make a pretty big difference in your model performance. And one of the things that I've found is that because kind of the default parameters for so many of these things are kind of built on these really big N kind of industry predictive models, the grids don't often line up all that well for like smaller N ecological problems. So I've often found that like the default values don't work all that well for me. And I need to kind of mess around with this stuff. And that can get really tricky, right? Because if you think about it, you've got a whole bunch of these things. There's often very little like intuitive sense as to like the values here. You know, trees are on scale of tens to tens of thousands, but learn rate is on a scale of like 1e to the minus 10th to like 0.1, right? So there's this kind of massive parameter space. They all interact. And so it can be pretty hard to kind of fine tune the values you're looking for here. And this is kind of why, you know, even though XGBoost, you know, will almost always be capable of beating a random forest, it's not always that easy to actually make it happen, depending on your kind of time budget to spend dealing with all this stuff. But it's neat stuff. So kind of the last one here, right, are neural networks. Random forest and XGBoost are great at things that look a bit more like regression, right? Predict numbers, classify categories, things like that. Neural nets are for when things start to get complicated. And in particular, they're really used for natural language processing, image processing, fun stuff like that. Fun fact, that's really not how the brain works. It's just kind of a name that caught on, but there you go. This is like a nice image of a neural net, right? You've got a picture of a cat. What it does then is essentially reprojects that picture of a cat into a new 1, 2, 3, 4, 5, 6, 7, 8, 9, you know, whatever that is, a 9-node layer representation of that thing, which it then reconstructs into things like an eyeball, a nose, and an ear, which it then collapses down into, if it's got these three things, it's probably a cat, right? And that's, you know, what a lot of neural nets end up getting used for. I was gonna like write out the pseudocode for like a bunch of algebra and this stuff, and I got tired of trying to write that out. But I think what's kind of interesting is like for all of the, you know, the voodoo and kind of craziness of neural networks, you know, they're kind of their guts at this. It's a bunch of matrix multiplication that basically takes, for example, if we started off with 10 observations and 2 predictors, you first develop a layer that retransforms that into a 10 by 5 matrix. You then come up with another let of weights that retransforms that back into a 10 by 1 matrix, which is your set of predictors and so on and so forth. You can see the problem here, though, pretty quickly in this little toy example, right? We had 10 observations and we have 13 parameters. That seems like a problem, and that's why we need testing data. My quick 2 cents on this, for a lot of the problems you're working on here, neural networks are probably going to be overkill. I'm just going to move on from that. We can talk about it later. Most of the time, if what you're doing looks like a regression and you're not like really deeply versed in this stuff, like XGBoost, random forest is probably going to be a better place for you than neural net. I've rarely had much success getting neural nets to work well without a whole ton of very specific work. And to kind of bring that all home, right, this idea, because I think there's this perception sometimes, right? Oh, there's a ton of models out there. And if random forest is the simplest and XGBoost is more complicated and neural nets are even more complicated than that, they must just kind of exist on this hierarchy like that. And so to kind of demonstrate this, I went back to, again, this kind of, you know, try and predict B over BMSY and RAM using just catch data. And I just kind of threw the most default values from random forest, GLM and Stan, and XGBoost, just checked them with all the defaults, tried to predict it, and then compared the performance, right? And on the left here, you can see that, wow, if we just looked at the training data, we would say, well, look at this. You know, my random forest model absolutely clean Stan's, you know, clock on this thing. No point for a structural model here. Incredible. When we actually look at the testing data, they all do just about the same, right? And so any differences in here are going to come down to kind of fine tuning these really finicky details. And this is why I keep saying, right, it's not as simple of kind of just subbing in Stan GLM for random forest, right? Things get more complicated than that. One of the big things we think about with machine learning models is uncertainty. We'll leave it at that. They don't do it for the most part. There's some cutting edge methods on that, but for the most part, if you really care about uncertainty, machine learning is not where you want to be. I'll talk about that later. Okay, so that was a really crash course in kind of the structure of machine learning models, but I think it's useful to kind of have an idea of what's out there and why these things work and how they work they do. But I think kind of going back to our motivating question here of understanding, right? This is kind of the thing we keep hunting for. Machine learning models are powerful tools because they can learn complex correlations that simpler models might miss, right? And kind of in a big way, the kind of point of this is that it removes the need for crazy factorial tables of interaction terms and polynomials, right? But obviously, there's no such thing as a free lunch. All that predictive power comes at a price, and that's understanding or inference, if you want to link it back to the opener. I think this comes back to two places. The first is just that it's really hard for us to visualize really complex multidimensional things. The second kind of goes back to fundamental problems of causal inference that I want to talk about for a sec here. But let's go back to that first thing, variable importance scores. You've probably seen these. The basic idea here is a variable importance score measures how often a given variable gets selected for use in a model, right? And so this kind of sounds a lot like a regression coefficient, right? Suppose that the true model is y equals 1,000 times x plus 0.001 times z. Well, clearly x is going to be a much more useful predictor of y than z, and so it's going to have a big marginal effect and a really high importance score. What I want to drive home here is that they are not at all the same thing here, right? So suppose we have a process model that looks like this, right? Y is 25x plus 50z minus 10 times z times w, right? X and z are real numbers. W is either -1 or 1. So we fit both those two models with the linear regression and a random forest, and then we compare the importance scores. So on the left here, these are our model coefficients, and lo and behold, right, we perfectly recover the coefficients, and so we were able to say, okay, z has the biggest marginal effect followed by x. W doesn't have any effect on its own, but it has a marginal effect conditional on z. But our importance scores look completely different, right? This says that W is by far and away the most important thing in this model, right? Because from the perspective of the model, it's a really clear breakpoint in which way the data are going, right? And so this is how kind of, an importance score can be a useful thing to look at, but it can really lead you astray if you're trying to kind of, sub it in and equate it as a marginal effect from a regression. We'll talk about this later if we have time. They can also help you a lot, though. If your linear model is very misspecified, a variable importance score can help you kind of tease out the fact there's something important about this variable, even if it doesn't show up in a linear model. Another big one are partial dependency plots. You've probably seen these. This is essentially trying to tease out the polynomial thing. It's like, oh, so instead of having to fit this crazy polynomial, we look at like species distribution as a function of depth, and we can see that, it goes up and down and it wiggles and it flattens out over there and all this cool stuff, right? And it can be really handy and just be a bit of a wet blanket, though. They can also be very misleading, right? Suppose that our true model is y equals 0.2 times x plus z, where x is a real number and z can be either -1 or 1. That's a pretty simple model. If we fit a random forest to that, though, and examine the partial dependency plot, we get this crazy looking thing here, right? Which says that, all right, the true effect of x on y, is this linear thing that just has a switch depending on z. The background is the partial dependency plot, though, which basically, if you were just kind of looking at that, you might think, oh, this means that, x has no effect on y, when in fact it has a total effect that the model does catch, but the effect is really hard to interpret without being able to visualize that interaction with z, right? And obviously, it's a simple example, and you could do that one visually, but it can get infinitely more complex as you go on from there. Okay, so crash course in kind of the structure of machine learning models, pointing out that, even if we want understanding, variable importance and partial dependency plots can help a lot. They're useful, but they're not the same thing. They're really kind of not getting you at understanding there. particularly if what you have in your actual model are a whole bunch of interactions, which is kind of the whole reason we want to do machine learning in the first place. I think kind of these things tend to be the importance, and partial dependencies tend to be the handiest if mostly what's going on is you've got a bunch of polynomials to your data. Then they can be really handy. Where they start to kind of get really convoluted is if what you've got is a whole bunch of interaction terms running around in your data. Okay, so with that then, we're going to take a brief aside into causal inference, right? So when I talk about machine learning with folks, right, a reaction to all this can be, what in the world, you know, we've got this crazy algorithmic model without these like really strong statistical inference behind it. We can't understand it. I'm just going to stick with my linear model, right, which makes total sense and I agree with. But I think we want to be careful about avoiding the trap of both poor prediction and poor inference. And to think about that, we got to kind of go back to causal inference 101, right? A common reason we stick with, say, a linear regression is that we can understand it. And so we would like to think we can make inference based on our results, right? But as we all know, correlation is not causation. Just the fact that we can estimate and understand a parameter doesn't really tell us whether or not that parameter actually causes the other one, right? And so a linear regression can obviously help us understand the former, the correlations, in kind of just a more visually intuitive way, but it's in no way guaranteed to give us the latter, right? And a large part of this is due to a fun little thing called omitted variable bias, right? So consider a data generating process of the form y is equal to beta 0, an intercept, plus beta 1x, plus beta 2z, plus an error term, right? Where error is IID, independent, identically distributed, right? Okay, so normal thing, everything's good there, right? Suppose our goal is to estimate the causal effect of x. What happens then if we omit z from our regression? Right? So if we just rearrange things a little bit, so now this is the true operating model. This is our regression model. Y is now just beta 0 plus beta 1x plus now u, where u is now this beta 2 times z plus our original error term, right? In order for our estimate of beta 1 to be causal, the causal effect of x, we need the errors to be conditionally independent of x, right? We need the expectation of u sub I conditional on x sub I to be 0, right? So does this now hold anymore? It holds under this case here, right? When epsilon is IID here, it holds. But now we're not talking about epsilon, we're talking about u, which is both these things, right? You can do some algebra and you can basically show that it's not, right? Or at least it's not conditional on this fun little term here, which is the omitted variable bias equation, which says that our estimate of beta 1, beta hat, as sample size approaches infinity, is going to be the true effect beta 1 plus the marginal effect of beta 2, which is the effect of z on y, times the correlation between x and z and this annoying thing over here. The important take home of all this is that no matter how many samples of n we collect, our estimate of the causal effect of x, beta 1, will always be biased proportional to the correlation between x and the omitted variable and the effect of z on the outcome y. The take home of this, right, this is why we can safely omit kangaroos from our Arctic char model, right? There's probably no beta 2 there. Beta 2 is 0, right? So we're good. We can also probably omit things that just aren't correlated, right? Maybe if we're trying to predict fishing effort, we might want to include both weather and weekend in there. But let's say we only have weather. We don't have any data on the weekend. That doesn't make any sense, but you get the idea. Both those things can affect fishing effort, but it's pretty safe to say weather and weekend are not correlated, though it probably seems like it sometimes. So we can omit that. But for lots of other things, right, this is why we run into a problem with linear regression and this kind of, our usual mantra of correlation is not causation, right? This is why stepwise selection is a very bad idea in regressions. As you omit correlated things, suddenly your variable of interest can magically become significant. It's not because you've teased something out, it's because you've soaked up through omitted variable bias all this effect into the thing you have left there. We can talk about some solutions to that some other time. So what's the solution to this? The best, obviously, is randomized control trials. Sure would be nice. The most common one is selection on observables, which is fancy speak for I've included everything that you could possibly think of that could matter in my regression. And this is often what is implicitly invoked in regression models, right? You know, a sentence in the paper like, we know that correlation doesn't imply causation, but look how well this one correlation lines up with our theory. We included a lot of other controls. And so if we were to interpret it causally, here's how we would. And the rest of the paper is all about that, right? I'm saying that 3 times in the mirror summons a grumpy economist as reviewer number 2. Just to kind of close that out, right? The Nobel Prize this year was awarded to David Card, Joshua Ingrist, and Guido Imbens for kind of their pioneering work on causal inference strategies using natural experiments, which are basically a bunch of ways for controlling for unobserved variables that could bias your estimates, that are invoked kind of simpler to assess assessment assumptions than we probably control for everything that matters. That was probably a tangent, but I think it's important to kind of bring it back to predictive modeling. All of that to say, right, clearly it's easy to say just because it's easier to interpret y is mx plus b, right, than a neural network, doesn't mean it's automatically giving us insight into causal mechanisms. And so in kind of this decision between a predictive model and inferential model, I'd encourage you to kind of take a step back and think about, you know, where and why are you fitting into those there, right? How can you think about coming up with a clear causal strategy to avoid kind of this pitfall of kind of poor predictive performance and poor inference, which can sometimes crop up a lot in the ecological literature. That's a really neat paper in 2002. I recommend you guys take a look at sometime. Okay, so that was a whole lot of stuff, right? But to kind of bring it all back together there, right? Predictive models can be any model. It's all about just kind of designing your framework in a way that's always designed around out of sample prediction and doing it in a way that's meaningful for the problem we're trying to solve. Within that, there are some ways for trying to kind of understand the parameters that you're dealing with there, variable importance scores, partial dependency plots, but neither of which is the same as a marginal effect in a regression. And even if you could interpret them as that way, I would again encourage caution in kind of thinking through equating simplicity of understanding, you know, the fact that a linear model is much more easy to understand than a whole bunch of interacting trees that our brains just can't process, right? With kind of the, have we actually identified a clear causal mechanism that we're teasing apart there, right? So with our final 10 minutes here, let's actually pivot back to kind of the original point of this project, which was salmon forecasting. So those of you who tuned out until now, welcome back. Okay, so the system we're looking at here is Bristol Bay up in Alaska here. This is the home of the largest and most valuable wild sockeye fishery in the world. The big thing you might notice here is that things have been changing. This is a graph of returns over time, broken out kind of by a couple of different ways of looking at it. Total returns, by system, and by age group here. And by kind of any way you slice it, the system has changed a lot over time in total volume, in the pattern of those volumes, in which river systems make up those returns, and in which age groups make up the returns to different systems, right? And this has caused a lot of problems since preseason forecasts are a really important thing for sockeye management and fisheries, right? In particular for the fishing industry, you need to be able to plan ahead and think through how much stuff you need to bring up to Alaska, how many people you need to hire kind of before the season, because you can't just kind of wander down to the store and buy a whole bunch more aluminum if you need to. Traditional salmon forecasting models are basically fit individually per age group and assuming independence per system. And they're generally based on sibling regression, right? Assuming a linear relationship between, say, returns of age 3 individuals and age 2 individuals. And this has worked very well for a long time. What we were curious about in this project was, can inclusion of models that allow for dynamics and interactions improve preseason sockeye forecasts? So the idea here, right, is instead of saying we have one model, which is in the Kvichak, right, we're going to predict 1-3s, and that's one model. We can say, well, we want to predict 1-3s in Kvichak, but it can be a function of 2-2s in Egegek and kind of, pink salmon out here in the open ocean, all these other complex things. And those relationships can change over time, right? So we looked at kind of 3 different broad classes of models: machine learning stuff, that was my kind of area; dynamic linear models, which was Curry's work; and empirical dynamic models, which is Peter Kuriyama's work. Both really cool areas of both predictive and inferential modeling. Talk about some other time. The regime we used here then, the goal is 1 year ahead forecast for each river system. So what we did is, starting in the year 2000, it generated 1 year ahead rolling forecasts. So for the year 2000, we included data from 1963 to 1999 in the training data. We then split 1963 to 1999 into a rolling series of analysis and assessment splits. For example, 63 to 85, predict 86, 63 to 86, predict 87. We then use those rolling splits to tune individual models, fit the best individual model configuration to that whole training split, so 1963 to 1999, use that to then predict 2000, and then move on to the next year to keep the process going like that, right? And then we repeated this for all of the candidate models here. In terms of model evaluation, then, we assess performance relative to a lag1 baseline model, where the forecast in year X is equal to the observed returns in year X minus 1. And so that's the scaled root mean squared error thing. This basically says that, like, the root mean squared error of this model was 70% of the root mean squared error of that lag1 model, right? So a 30% improvement, right, in percentage points. So take home thing here, right? We saw some substantial improvement over kind of the baseline lag1 model. Some worked better than others, like the multi-view, that empirical dynamic modeling worked really well for the 1.3s. Boosted trees did better for 1.2s, so on and so forth. But then to generate a forecast, right, we're faced with a bit of a question. We have multiple models, and we need to kind of pick which models we want to use for what age group and system. So the way we decided to do that was then to generate kind of a super ensemble model on top of these things based on past performance. And this is what the Fisheries Research Institute has historically done, but kind of more qualitatively. So what we did is we assessed the performance of each model from 1990 to the current year in a kind of a rolling fashion. We then trained an ensemble based on the historic performance of each individual model. So essentially, it's a dynamic weighting of individual models rolling forward over time, and then generate the forecast by system and age group using the ensemble model. So if we want to use the ensemble to predict 2020, it's based off of the historic performance of the other models from 1990 to 2019. And this is kind of what we found, right? The circles here mean that the random forest ensemble was the best ensemble for that river system. The triangles mean that the traditional qualitative-ish FRI method was the best for that system. So the ensemble provided no improvement. So there's a couple interesting takeaways here. One is that, there's variation by system. Two is that, there's definitely systems where all this crazy fancy new modeling, right, didn't really improve much on what's already been happening in places like Ugashik. But, we're able to see some improvements kind of on the order of 15 to 20% in places like Egegek and Kwijak, which are neat. But what I think was kind of the most interesting outcome from this project is kind of helping us identify when the problem is kind of we didn't use the right model, right? There's a different model specification or a modeling tool that might do better, versus the idea that model specification probably wasn't the problem, right? The information to make a good prediction probably wasn't there in that year. So what we're looking at here are standardized residuals over time by river system. And what's important is, there's a couple systems like the Nushagak here, right, where they're just kind of bouncing around zero, right? All the models are kind of doing pretty similarly. But then we see these years here, like the Wood, for example, where all of a sudden every single one of the models just falls flat on its face in a very big way, right? And what we think this is telling us, right, is, again, the question here was not, the true operating model was X squared plus the square root of Z plus, that times that. The problem here was that with the data that we had, something happened that produced this massive spike here that just wasn't in any of these structured models' ability to kind of come up with there. And so what we're kind of hunting around for now are data that might, point at something weird that kind of happened here that we might be able to build in to fill in the gap here. So again, the point here of being a case where if we want to make a better prediction here, we probably need better data, not a fancier model. So kind of thoughts on the overall salmon process here, right? Across model differences are small and probably more chance than structure, I would argue. For machine learning, one thing we didn't talk about here, but feature engineering makes a huge difference here. And this is why, we talk a lot about the importance of, like, pairing the engineering side with the subject expertise side and thinking about how do you structure your variables in a way that sets the models up for success. In this case here, kind of using a bunch of highly flexible models helps rule out probably model misspecification as an explanation for poor forecast. It helps rule out, well, we modeled it as y equals x, but it was really y equals x plus x squared, and that's kind of the problem, right? And kind of allows us to focus in on what went weird in some big years there. Kind of my big take homes in all this, right? Again, any model can be a predictive model, but a predictive model requires a fundamentally different workflow than an inferential model. It's not as simple as just replacing LM with Ranger or Random Forest or XGBoost or whatever. If we don't care about inference, machine learning models can be a powerful tool for finding kind of these hidden predictive structures. But if we care about the why at all, there can be a problematic aspect to them right there. A way that I kind of like to view these things is using these kind of big predictive models to help you find the predictive limit of your data. If you have like a really strong structural theory of your data generating process and you kind of want some prediction from your model, it can be good to kind of do a horse race against those two and see, well, if the structural model is basically as good as the machine learning thing, great, get your prediction and get your inference, right? But if the structural model is just way worse of a predictor than your machine learning model, it might still be worth sticking with the structural, but worth kind of thinking about, maybe that's telling you that your structural model has some problems with it. And I'll just briefly mention here that synthetic controls are kind of this interesting new econometric technique. It's kind of a blending of these two cultures. Neat thing, talk to me sometime about it. At the end of the day, machine learning is not magic. It's another useful tool in your toolbox, use appropriately. I will highlight that then with this fun video, which I think highlights, kind of both the promise and silliness and big problems with machine learning, right? It's able to power an algorithm that can vacuum our house for us, and yet it can be easily fooled by a black line on a carpet. So with that, that took quite a while. There was a lot of information, but hopefully we have time. Folks can stick around and we can do some questions, and hopefully I have some answers. Thank you.
Awesome. Thanks so much, Dan. That was fantastic. Looks like you got a couple questions in the chat. Can you see the questions? I'll let you take them if you can, or I can read them to you.
I cannot. I see questions, I see chat. I see nothing in either questions or chat.
Okay, then I will, oh, you know what? Here's what I'll do. Now do you see a question?
Yes, I see one from Will here, yep. Yes. So Mark Sherrell's question is basically for Bristol Bay sockeye. Do you fit forecast each age group separately, or fit forecast as a multivariate group to take advantage of shared process observation errors? It's a great question. So if I interpreted that question correctly, and Mark, let me know if I'm incorrect here, right? At the moment, we're kind of treating it like a very classic regression, right? The goal is predict 1-3s in this one river system, right? But you could extend that and kind of make it a multivariate prediction problem where you're kind of simultaneously predicting like 1-3s, 1-2s, all the stuff across river systems in kind of one go, right? We tried some versions of that. It didn't work particularly well. I think, with infinite sample size, it would probably be the better way to go for the reasons that you talk about. But I think with finite sample size, it's asking a lot of the model to kind of disentangle all the intercepts and things that it kind of needs to do to kind of tease all that stuff apart. At least that's what we found so far. But I think it's a great idea, and I think it's something to kind of focus in on a little bit going forward. Are there kind of compromised models in between there? Though again, one of the things that we found in the machine learning stuff, right, was while it wasn't the outcome, including those things as predictors helped a lot, right? So it's saying that, other age groups and other systems help you predict a current system. That does build that correlation structure in there. And it was a really useful predictor for us in a lot of cases. So hopefully that answers your question, Mark. Let me know if not. All right, just kind of going down the list here. All right. Oh, Jimmy, I always forget to include this in the sockeye thing. Jimmy and Ellie asked, leaving off 2021 for sockeye predictions, how'd it go for this year? That's a great question. So for those of you who keep track, we had an absolutely record-breaking sockeye returns to Bristol Bay this year. I think 67, 68 million fish. The machine learning stuff, the stuff we kind of developed here, did better than some of the other ones, and that it predicted a big year. But I think our prediction was something like 54 million, which was a lot higher than some of the other ones, but obviously still it was not close to 68, which is on nothing's radar. And so I think that's going to be another fun example. What we have noticed is that some of these, predictive style models have done a better job at picking up the fact that things are increasing lately, in particular the 1.2s and the 1.3s, and they seem to be on an upward trajectory. Whereas, as you might expect, some of the more statistically models really want to kind of pull things back to kind of, the average there, when something in the data seems to be telling the predictive models that things are still heading up somewhere in there. Okay. There's an interesting link to a paper here. Stop calling everything AI, machine learning, etc. I'll have to check that out. But yes, I absolutely agree with that. I think it's a really common thing. If you want to make your method sound really fancy, call it, an artificial intelligence approach to blah, when what it was a slightly fancy regression, right? And I think, we'll be served by kind of demystifying some of these things. Even the machine learning side of a random forest or a boosted regression tree, that pseudocode's not too complicated. The devil's in the details there, right? But they're not magic, right? They're, fairly simple-ish algorithms where a lot of the complexity is in efficiency and all that kind of stuff. And, I think it helps us put them in context that they're useful, but complicated. Let's see. Your residuals for NAC were uniform. I think this is from Hassan. I think this model behaved well because of absence of the spike between 2015 to 2020 in your data, right? Yeah, absolutely, right? So, right, if you're looking at NAC, right, part of it was just that, like, NAC was kind of well behaved for a long time. It was kind of just, up and smooth and not that crazy. Though, I mean, there was kind of this period back here where, you could kind of view that as a pretty similar ramp up. But I think the big difference there is, for whatever reason, the model was kind of capturing that ramp up fairly well back then, and then it kind of didn't too well here. I don't quite know what that's about. And yeah, that's kind of a big question in all these things, right? Especially in systems like Alaska, where the system is changing very quickly. An advantage to these dynamic models is that you can include the past while learning from the recent past, right? So you're not stuck in saying that, even if 1970s are not the way the system works anymore, you can still include them in your model and, use that to learn a little bit. But there's an open question there, right, of like, how fast can these things pick up, right? And what you'll kind of see in here is a lot of times there's a lag there, right, where it's like it's going along, something big happens, then it pretty quickly adjusts to the new regime. But it's pretty hard for a model to kind of a priori pick up these massive spikes kind of just out of the blue, right? And I think with climate change, it's going to be a big thing that we're kind of looking at here. Ooh, man, a lot of questions. Question from Trevor. Hope you're writing a nice review paper on this. Yep, that's what Caitlin is leading, and she's doing a lot of cool stuff on this. And I'm kind of diving into some of the nuances and the problems of ecological data sets in particular. Which I think is going to be really helpful because, so much of the literature on this is, assume you have, trillions of data points, right? And kind of that's not what we have. And in particular, we tend to have low N and really, really complicated, spatial temporal correlations. Yeah, so Jim's asking here about relative weighting. So the idea here that some predictions may be much more important than others. And that's something we definitely talked about a lot in the Bristol Bay system, right? Should the point even be dialing in the numbers, or should it be like avoiding getting it really wrong, right? Or maybe we really want to emphasize on getting big years right and kind of care a little bit less about small years wrong, or vice versa, right? It's something we've thought about a lot, and it's something that actually comes in a lot in your consideration of the objective function for these algorithms. For example, depending on whether or not you choose root mean squared error or mean absolute percent error is implicitly kind of doing that, whereas one kind of really downweights kind of getting really root mean squared error emphasizes not getting really big things wrong. Mean absolute percent error kind of emphasizes not getting really small things wrong. And so that is a very important one for fisheries, and I think an interesting one to kind of focus in on here. Christine asked, is there a recommended way for deciding where and how big to make the rolling window splits? I haven't seen great guidance on this, and I think this is going to be a fun thing for us to discuss in our paper, right? Because again, so much of the literature is based off of, things that don't look like our systems. I tended to focus on, again, what's kind of the time window you're trying to forecast out to. And kind of that's why we focused a lot on kind of the 1 year ahead thing. But maybe for like, if we were trying to do this for, say, predicting recruitment for like projection in a stock assessment, we might want that window to kind of be pushed out a lot further. In terms of how far back to go, I'm usually pretty greedy with that, and that these models take data. And so, the more you can kind of pull in conditional on the past looking nothing like the present, the better, as long as you kind of help the model along the way with like having a variable in there to track time, for example, that can kind of help it build interaction terms in that can tell it to say, change the slope of this parameter over time. Man, a lot of questions. Charmaine was asking, if we had better data, based on your work, do you now have suggestions for better data? If so, can you give examples? I think a big question for us is kind of getting some more information on what's going on out in the ocean phase. One thing we noticed is that the thing that kind of the less structural models have been better at predicting are like the 1-3s. But if it was just an age thing, it doesn't really make sense why they'd be better at the 1-3s, but not at the 2-2s, right? They're the same age. But the 1-3s are spending more time out at sea. So maybe there's a process out at sea that's kind of inducing this change of kind of more fish coming back as 1-3s instead of 2-2s, for example. So I think at sea data would be the great thing for that. So I'm sure folks with much more salmon expertise than I have comments on that. Ian Stewart asks, how would you suggest avoiding the identification of a spurious predictor of those few anomalous years, since now the residual sample size is only 1 to 2? Yeah, that's a great question. I'm not sure if I'm understanding it exactly. I think with all of these things, right, that's kind of the question in here, is the signal to the noise, right? And that's kind of part of the reason for those big rolling assessment analysis splits, and kind of trying to, in the machine learning models cases, tamp down the model's excitement for new data in there, right? So, if you, for example, crank up the learning rate of a boosted regression tree, it's going to just kind of like grab onto every little kind of nook and cranny in the data. And that will show up as really bad cross-validation in your assessment and analysis splits. And so by kind of finding the value of those parameters that seem to give us the best performance in the analysis and assessments, that's what gives us the most confidence that the model's not going too crazy and just kind of grabbing onto whatever the most recent thing is. And we have some plots in the paper kind of projecting that forward, right? So if you only fit through 2001, we're looking at 2001, but you can keep that forecast going, just not updating the model fit to like 2020. And you can see that most of the time it actually works fairly well, which gives us some confidence that we're not overfitting it too much. John Wallace asked, why are the salmon numbers up? Man, I wish I knew. I'm sure other folks on this call can give you a much better answer. I think it's a really complex mix of things going on in the river systems, things going on in the ocean phase. This is Bristol Bay we're talking. If you look down in the Gulf of Alaska, we're seeing a very different story. So, I do not know. I wish I knew. I do not. I think there's a lot of really fascinating research to be done, trying to kind of figure that out for salmon and for a lot of other species up in places like Alaska, where climate change is happening really fast and a lot of species are changing quickly. Man, I'm going to need some tea after this. Okay, I think that's all the questions in the chat. I'll pause there. It's always so weird just talking into the void on these things. I don't know if there's any other questions, comments, concerns. I know we are over time.
Yeah, thanks, Dan. That was great. There are a couple more questions that I can assign to you. We are over time though, so folks have to go. But if you have a minute to answer them so that they're up on the recorded version of this talk, that would be
Yeah,
awesome.
absolutely. Yeah.
Okay, I will send them your way.
Let's see if I can. Is there a way to? I think I can. If I hit the trash on these, are they like recorded?
Um,
Which ones I've already
Good
done?
question.
Okay. Um, okay, Lychee asked, it's hard to imagine a more data-rich fishery system than Bristol Bay sockeye. Do you, off the top of your head, see these methods being applicable to any other fishery in the world? I mean, that's a fantastic question. And I think, that kind of goes back to, it's like fisheries in general, it's hard to imagine a system we can study better than this. And you look at this pattern, whether it's a machine learning model or whether it's a surplus production model, right? It's pretty clear there's a lot of stuff going on in here that we're not that well equipped to handle at the moment. I mean, this is an incredibly data-rich system. I think, there certainly are other fisheries, but I think in many of these cases, it's going to come down to kind of substituting width for depth. So instead of kind of long time series for individuals, right, we're going to kind of be having to like get data from a lot of different fisheries and see if we can pull them together and kind of use that to get our sample size up. But yeah, no, I think that's a fundamental problem with a lot of this. And, I think, as many of you might know, I've spent a lot of time having to like squint at relationships between catch histories and B over BMSY. And, it's a long time series, it's tens of thousands of observations, depending on how you kind of structure your data. And, it just kind of plateaus at a certain point. There's just not that much information in there, at least from a predictive power perspective, which, we've got a couple papers coming out there. And I think, yeah, I think that's where structure helps us, right? I think kind of focusing in on theory and kind of saying that, right, well, in a lot of these systems, we can't just kind of count on the machines to kind of solve it just because they can theory can wiggle around a lot. And that's where, having a principled model informed on theory, can go a long way on kind of helping you squeeze the most information you can out of much shorter and messier data sets. That's my 2 cents. Hassan was asking, kind of related, are you planning to continue using machine learning or go back to traditional ways of doing things? I mean, I do both, right? And I think, again, I break it down into prediction and inference more than machine learning versus not. I think there's a lot of questions where predictive questions are interesting, species distributions, big return things, maybe recruitment and some things like that, right? Fleet dynamics are an area I spend a lot of time thinking about, where maybe we just want to see if we can make better predictions. And then where I like to be able to live is kind of this intersection between the two, where we can kind of, compare really theory-driven predictions to these kinds of things to kind of get a sense for, how well does our kind of simple representation of, let's say, fleet models using an ideal free distribution, how well does it actually stack up to a predictive model given the data we have there, right? So, I use them. I think they're great. I think they're really interesting. They're just another tool, and it's a good thing to have in your back pocket. I think conditionally on doing them well. You'll notice there were no neural nets in this project, and that's because I spent a long time trying to get them to work well and just never got it to the point where they were working well or as stable as the other ones. So I might avoid those for a while with these kinds of problems, but maybe that's just me. Howard Stiff asked, does machine learning deal with or adjust for autocorrelation in the time series better than typical parametric analyses? Maybe. It's hard to say better, right? Like, it's easier to build them in and allow them to be complicated. So what you can do, for example, right, is essentially, a inferential or a parametric analysis, right? We can make an AR blank process, right, where we include lags 1 year, 2 year, 3 year, 4 year, 5 years ago, right? You can do the same thing with the machine learning model. The advantage there is that a machine learning model might help you learn like which one of those lags are the best predictors, whether or not that changes over time, and whether there's complex interactions, right? So maybe it's like there's some weird autocorrelation between like lags 1 year ago and 6 years ago, and like it's the interaction of those two things that really matters that can kind of help you find that, right? But again, there's nothing structural in this stuff, right? And so I think that's where kind of that sweet spot of kind of that feature engineering of thinking about, rather than with a finite sample size of just feeding, every single possible lag in there, we can have some thoughts about, well, we know the life cycle of salmon. We kind of have a sense for probably like how many years back of a lag might be reasonable here, and kind of help use that to guide things, right? So I don't think it's better in any way. And I think, structural stuff might do a better job if the system is changing really rapidly and your model is like latching on to noise more than signal, in a similar way that like, a shrinkage term or a lasso or a prior, whatever you want to call it, depending on your modeling framework, can help pull things back towards sanity. A structural model might help you with autocorrelation there. Jimmy Anelli says numbers are up because of pollock recruits. That makes as much sense as anything to me. It'd be really cool to get some data on that. All right, I think I think that's all of the questions, the new ones that came up there. Yeah, like I said, be on the lookout. Salmon paper should be hopefully getting back out there soon. Like I said, look out for the paper that Caitlin's leading, kind of linking all the stuff to ecology. I'm always up to talk about these things. I don't have much formal training in this. I have some, but a lot of this is trial and error and reading a lot of books. And I think maybe kind of because of that, like like if I was sounding, all the things I was pointing out before are kind of issues that I've discovered because I messed them up earlier, right? And so then you kind of learn from your mistakes. So always happy to kind of talk about this stuff if anyone's interested. And hopefully the recording will be up, and I'll post these slides somewhere. It's a little convoluted where they live right now, but yeah.
Great, thanks again, Dan, so much. That was great. So if you're still with us, join us next week for Brett McClintock, who will be presenting, let's see here, an integrated path for spatial capture, recapture, and animal movement modeling.
Cool.
Great, and then with that, I will end the recording.
Okay, are we recording?
Yep.
Oh, it says being recorded. All right, cool. Thanks, everybody. I'm Dan Ovando. We're going to be talking about tools and strategies for predictive modeling, with a focus on machine learning and salmon. Before we get going here, the ideas and results here are the result of a collaboration with two fantastic groups. In particular, this working group, Issues and Best Practices in Machine Learning with Ecological Time Series Data, led by Caitlin Allen Axelrod, with Curry Cunningham, myself, Christine Staywitz, and Jordan Watson. The salmon work is with myself, Curry Cunningham, Peter Kuriyama, Ray Hilborn, and Chris Boatwright. And the salmon forecasting work was funded by the Bristol Bay Regional Seafood Development Association, the Bristol Bay Seafood Processors, and by Douglas and Joyce McCallum. So huge thanks to all those collaborators and funders. To kind of motivate all this, right, I think there's this neat paper by Leo Breiman in 2001, who some of you might recognize as the original author of the random forest method. And he talks about this idea of there being two cultures in statistics, right? Inferential modeling, which is what the vast majority of academic statistics is focused on. What is the effect of X on Y? And is it significant enough for me to publish, if that's what you care about? And this is kind of the realm of questions like, why does it rain, right? And this is where, I think most scientific work kind of lives. But there's this kind of parallel branch of what we might call predictive modeling. This is what industry spends a lot more time doing. And this is thinking about things like, can I predict Y using X? And is the prediction good enough to be useful? And this is more kind of, will it rain as opposed to why does it rain? Are we good? Yep.
This is where we stopped. Thank you so much. I'm really sorry about that.
That's super funny.
Yeah, like I said, we're just getting the hang of it still.
It's tricky. Yeah, this is fine. Yeah, cool. All right. Hopefully I got enough equations in there to qualify as a quant sum. I feel like that's why I went down the causal inference route, because I thought I'd get disbarred otherwise. But
oh no, it was one of the most well attended, and I've never seen so many questions. So
yeah,
you were really.
People do like machine. If nothing else, hopefully less people wite artificial intelligence in their abstracts.
Sure. Yeah, or big data, things like that.
I have such a pet peeve with that. Yeah. Artificial
All right,
no problem. Used a random forest. Okay. Anyway.
Yeah. All right. Well, enjoy the rest of your weekend, and I'll shoot you an email with a couple of housekeeping things, and your talk should be up in a couple of days. I'll stitch the.
Thanks again. I never responded, but yeah, great talk last time. And yeah, I would definitely love to pilfer your Zeringan code at some point since it looked absolutely beautiful and like.
Oh, thank you. Yeah, I will get.
Just like using the
get on it.
days, but yeah.
Okay, sounds good.
All right. Thanks, Abby. Bye.